Hello everyone. So in this video we are going to discuss about two basic signals, that is unit impulse signal and unit step signal. So in this lecture we will see the definition of these two signals and how they are related and how from one signal we can get the other signal back. So these are some points we will discuss in this lecture. We are reading these two kind of signal because they are of considerable importance in signaling system, and we will see that how impulse signals can be used as a basic building block for construction and representation of other signals, and they are quite useful when we discuss other topics in this subject. So we have two parts. First we will discuss about discrete time case, and next we will discuss about the continuous time case. So first we will going to discuss about the discrete time case. So let's see the definition of unit impulse signal. So unit impulse signal is basically defined as del n, which is equals to 0 when n is not equal to 0, and it will take a value of 1 when n is equals to 0. So this is the basic definition, and how we can visualize it. So we will plot a graph. Here this axis represents the n value. So for n is equals to 0, it will take a value of 1, and for all other values of n, the value will be 0. So these are the value 1, 2, 3 and so on. These are the value -1, -2, -3 and so on. So this is the definition of unit impulse signal. Next we will see the definition of unit step signal. So unit step signal, as the name suggests, it has a step. So first we will define and we'll see how this step looks like. So we have the definition of unit impulse signal as un, and it has a value of 0 when n is equal to when n is less than 0, and it will take a value of 1 when n is greater than or equal to 0. So I am pretty much sure that you can visualize it quite easily. So this is your n axis, and this is the value of n equal to 0, and all these values are greater than n equal to 0. So this signal will take a value of 1 for all value greater than or equal to 0. So it will take 1 for all these values, and for value which are less than, for n value which are less than 0, it will take 0. So this is a unit step signal. Why we say it is a unit step signal? So if we trace the envelope of this signal, you can see that these are all values as 0, and then there is a sudden jump, and then all values are 1. So it's a kind of step. So step is happening here. So that's why it's called a unit step signal. This is quite clear when we discuss about the continuous time unit step signal. So now next we'll discuss about the relation between these two signals. So suppose if we have the impulse signal, how we'll get the unit step signal, and if we have a unit step signal, how we'll get a unit impulse signal. So we'll first discuss the relation of del n. So del n can be obtained by taking the difference of un and u of n minus 1. So this expression is very simple, and when we try to understand it using the graph, it will be more simpler. So how we can visualize it? So we know that how un looks like. So we have this n axis, and for all values which is greater than or equal to 0, it will take a value of 1. So this is the plot of unit step signal. This is u of n. Now we have already studied the shifting property. So we want to plot of u of n minus 1. So how we can plot? Yes, you guessed it right, that we will have to shift our signal to the right by 1 unit. So now the signal will look like this. So this is n equal to 0, 1, 2, 3 and so on. And when we will take the difference, so we will take the difference between u of n and u of n minus 1. So what will happen? All this signal, so this will be subtracted by this will be subtracted by this, and all these value will vanish. Only the value at n equal to 0 will be left. So what we will get at the output? So it will be 1 at n equal to 0, and for all other values it will be 0. So this signal basically resembles del n, as we have already discussed the definition of del n. So it will take a value of 1 for n equal to 0, and for all other value it will be 0. So in this manner, this expression will give you the representation of unit impulse signal. Next, we'll see how we can obtain the unit step signal from unit impulse signal. So this is also a very simpler expression. So we will take the running sum of our unit impulse signal. So what is this expression? It is summation m varying from minus infinity to the n value, and we'll take del m. So first, to visualize it, what we'll do, we'll first plot the del m function. So del m function will be a very simpler representation. So for m equal to 0, what will be the value? It will take a value of 1, and for all other values it will take a value of 0. This we already know. So this is m axis, and for m equal to 0 the value will be m. So this is a plot of del of m. What we are doing, we are taking the sum by varying m from minus infinity to n. Now there are two cases here. N can be greater than 0 or n can be less than 0. So these two cases arise. So suppose we will take the first case. So suppose we are taking n greater than equal to 0. So in that case, the envelope will look like suppose we are taking some n value, so this is your n, and this n is greater than 0. So what will be that sum? Yeah, exactly, it will be 1. So because for any value which will take greater than 0, it will take this signal in that range. So for every value of n which is greater than 0, greater than equal to 0, the output will be 1. And if we will take the envelope n less than 0, so how the range will look like? Any value which is less than 0. So the output will be 0. So suppose we'll do that summation m equal to minus infinity to n del m. So for all value which is less than 0, the value will be 0, and for all values greater than equal to 0, the value will be 1. So indirectly what we are getting? We are getting our unit step signal back. So in this manner, this expression can be a representation of unit step signal in terms of unit impulse signal. This is one way of representing unit step signal. We can also have like a different expression, and which is quite evident. So we can have a approach using the time shifting operation. So we can say that our unit step signal can be written as summation of shifted versions of unit impulse signal. So here what we are doing, we are taking k equal to 0 to infinity and we are shifting the signal by that k amount. So if I will write it in an expanded form, how it will look like, it will be del of n plus del of n minus 1 plus del of n minus 2 and so on. So if we'll represent all this in a single plot, how it will look like, for n equal to 0, it will have a 1 because of this signal. Then we are adding another signal which is n equal to 1. It will take value of 1. So this is this signal. Then we are shifting the signal by 2 amount, that is del n minus 2. So at n equal to 2, it will take a value of 1 and so on. So indirectly what we are getting the unit step signal. So this will be your un, and which is actually summation k equal to 0 infinite del of n minus k. So shifting property also can be used to understand this relationship. Next, we'll discuss about one of the property of unit impulse signal. So the unit impulse signal can be used to sample the value of a signal at n equal to 0. So for sampling any signal, we can use our unit impulse signal. So how it can be done? So we can have any signal xn, and when we will multiply that signal with a unit impulse signal, what we'll get? We'll get the signal value at x is equals to 0 multiplied with the impulse signal. And more generally, if we want to consider a unit impulse signal, del of n minus n naught at n is equals to n naught, then we can write x of n del of n minus n naught is equals to x of n naught del of n minus n naught. So basically what we are doing, the unit impulse sequence is used to sample the value of a signal at n equal to 0. So this is the case. So this is a very important property, and this is called the sampling property of unit impulse signal. So this is your sampling property, and this will be used subsequently when we'll discuss some other topics.